All right, so when we're trying to figure out a product's environmental footprint, we end up with this massive pile of data. Lists of emissions, resources used, you name it. But what does it all mean? How do we get from a raw spreadsheet of numbers to actually understanding the potential damage? Well, that's exactly what life cycle impact assessment is designed to do. So here's our game plan. We're going to start with why we have a data problem in the first place. Then we'll look at the framework we use to solve it, breaking down the two essential steps: classification and characterization. We'll also unpack the crucial difference between midpoints and endpoints. And to wrap it all up, we'll calculate the true environmental cost of a simple steel spoon.
To really get a feel for this challenge, let's start with something super simple. Imagine you've just done all the hard work of a life cycle inventory, or LCI, for a basic steel spoon. You've tracked down every single input and output from cradle to grave, all the resources, all the emissions.
What you get looks something like this. It's a long list of all the different substances released into the environment. We can see, just over a kilogram of CO2, a few grams of methane, a tiny bit of nitrous oxide. And trust me, this is the simplified version. A real inventory could have hundreds of data points just like these.
And this, right here, is the million-dollar question. You're staring at this scientifically accurate list of chemicals, but what does it actually tell you? What's the story? On its own, it doesn't really answer the most critical question. What's the potential environmental impact?
So to make that leap from just a list of numbers to genuine, actionable insight, we need a specific, really powerful framework. And that framework is called Life Cycle Impact Assessment. The whole LCA process is actually standardized by ISO 1440. It's broken down into 4 key phases. And the one we're zeroing in on, the one where all the translation happens, is this critical third phase, the Life Cycle Impact Assessment, or LCIA. This is where the magic happens. The whole point of the LCIA is to take that long, frankly overwhelming inventory of emissions and boil it down into a much smaller, more manageable set of potential impact indicators, things we can actually wrap our heads around and use to make decisions. Now, the ISO standard lays out a few steps within the LCIA process itself. Some of them are optional, things like normalization and weighting, which can help you compare different types of impacts. But for today, we're really going to focus on the 2 mandatory steps. These are the absolute cornerstones of any credible impact assessment. The first mandatory step is classification, and you can think of it exactly like it sounds. It's a sorting process. We take every single substance from our big inventory list and we assign it to the environmental impact categories that it contributes to. And this visual lays it out perfectly. On the left, you see our emissions: CO2, methane, sulfur dioxide. And we're basically just drawing lines linking them to the right impact buckets. So you can see both CO2 and methane get sorted into the climate change bucket, while something like SO2 goes into acidification. Simple as that. Okay, so we've sorted everything into the right categories. Now, for the really crucial part. We need to figure out just how much each of those substances is actually contributing. This step is called characterization, and it's all about understanding the relative power or potency of each emission. So here's the key idea. You can't just add 1 kilogram of CO2 to 1 kilogram of methane and get a meaningful result, right? They affect the climate in totally different ways. So we have to convert them into a common unit of measurement, an equivalent, before we can add them up. So for the global warming category, our reference unit is CO2 equivalents. Makes sense. For acidification, which leads to acid rain, we use SO2 equivalents. For eutrophication, that's the over-enrichment of water, we use phosphate equivalents. Every single category has its own reference substance that we measure against. The calculation itself is pretty straightforward, really. It's a simple 3-step process. For every substance in a category, you look up its unique characterization factor. You multiply the amount you have, the mass, by that factor. And then you just add up all the results to get your grand total for that impact category. So what do these factors actually look like? Well, for methane, its characterization factor for global warming, measured over 100 years, is 25. What that means is that 1 gram of methane has the same warming effect as 25 grams of CO2. It's 25 times more potent. And then you have a substance like nitrous oxide, which is an absolute powerhouse. Its factor is 298. So releasing just 1 gram of N2O is like releasing almost 300 grams of CO2 in terms of its impact on climate change. You can see how these factors are absolutely essential to the whole calculation. Okay, But there's another layer to this that's really fascinating. We can actually measure these impacts at two different levels along the environmental cause and effect chain, and we call these midpoints and endpoints.
Think of it this way. Midpoint indicators are problem-oriented. They measure things like global warming potential. They're scientifically solid, they're close to the original emission, and there's not a lot of uncertainty. Endpoints, on the other hand, try to measure the final damage to things we actually care about, like damage to human health or damage to ecosystems. They're much easier to understand, but trying to connect one emission to one specific health outcome involves a lot of modeling, which means more uncertainty.
This flowchart shows that relationship perfectly. Our raw inventory results are characterized into these midpoint categories, like global warming potential. And that potential then contributes to an endpoint damage category, like climate change, which ultimately affects human health and ecological quality. It's a whole chain of events.
All right, theory time is over. Let's put all these pieces together. It's time to apply this whole framework back to our simple steel spoon and finally get an answer to that question we asked at the beginning. So here's the calculation for our global warming potential midpoint. We take the mass of each gas that we found in our inventory, we multiply it by its specific characterization factor. So 1 for CO2, 25 for methane, and that big 298 for nitrous oxide. And that gives us the total impact for each gas, all in our nice common unit, kilograms of CO2 equivalent.
And here's our answer. When you add up those individual impacts, the total global warming potential for the entire life of our one steel spoon comes out to 1.24 kilograms of CO2 equivalent. We have our number! And that is the real power of the LCIA process. We've gone from a long, confusing, frankly useless list of chemicals to a single, scientific-based number that's understandable and actionable. With this one metric, a designer can compare materials, an engineer can optimize a process, a manager can evaluate suppliers. It transforms complex data into a powerful tool for making smarter, more sustainable decisions. This whole process, this methodical classification and characterization, it allows us to peek behind the curtain and uncover the hidden environmental story inside every single product we make and use. So the real question is, what story are you going to uncover next?